Hello, welcome to the first webinar in our webinar series. We have a series of 6 webinars going this summer, every week at this same time, every week for the next, today and then the next 5 weeks, covering how to use Hexagon simulation software for formula. I'm going to give a lot more information on that in a few minutes. I mean, near the end of the talk, that is, and telling you how to access our software for free. I'm going to now introduce our presenters, and then we're going to get into the webinar. I am so excited. Thank you so much for coming. It is just amazing to see all the people who are interested in learning how to do CFD on a formula vehicle. And I should say a lot of this material would be equally valid for Baja or other similar competitions. Supra comes to mind. So with that, let me introduce Shiraz Butt. He is a recent graduate. He joined Hexagon within the past year, and he is a technical specialist. He supports our customers resolving inquiries regarding our CFD simulation software, Cradle. And during the Q&A time, we're going to have another engineer on the line ready to talk to you, help field any questions. He's extremely experienced. It's Rodrigo Auza Gutierrez. And again, he's another technical specialist working on Cradle. He has, sorry, my mic just cut out for a moment there, I think. 6 years of experience in CFD, working in ground vehicle aerodynamics and aeroacoustics. So that's experience that is extremely relevant to, the job to be done here. So with that, Shiraz, why don't you get started? I'll go off camera. You pull up your slides.
Perfect. Thank you, Alex, and welcome everyone to this webinar. I'm very excited to hear you working in such a challenging and exciting project such as the SAE Formula Design Competition. And today I'll be presenting about how you can use Cradle CFD to support your design in today's session. So let me start by sharing my screen with the slides. And if you could confirm you're able to see them. Okay.
I see the slides. Everything looks great.
Okay, so in today's agenda, I'll be starting by introducing Cradle very briefly. And from there, we'll be jumping into the demonstration where I'll show you a step-to-step process of setting up the model of a rear wing formula vehicle and how to apply all the conditions, make the domain, apply the material properties, and finally how to post-process the results. And additionally, I'm going to show you briefly how to create a modification of the geometry by tilting the rear wing by 8 degrees and running the simulation and comparing the results. And I will also make a brief comments about how you can set up a full model vehicle. And finally, we will have room for some questions and answers, and my colleague Alex will be detailing you how you can access the software. Okay, so we can move on into introducing Cradle. So Cradle is a general CFD purpose software. It is part of the Hexagon Manufacturing Intelligence Group since 2017, and it was founded in 1980s in Japan. And some of the key features of Cradle can be explained by this imaging here of a Japanese katana. So some of the attributes are that is a practical and strong and very sharp tool. And what I mean by this is that Cradle has a very simple user interface that can allow you to run any type of cases, whether you're looking for simple ones or more details. And thanks to its strong meshing capabilities, you're able to run your simulation within a relatively short time. And thanks to its very powerful post-processing tool, you can visualize your results and create animation and many other type of visualization images that I can show you later. Okay, so in general, Cradle CFD is divided into 2 modules. Those are SC Stream and SC Flow. The differences between the two is related to how the mesh is generated. For SC Stream, we're going to use orthogonal structure mesh. where you can apply a very large number of components, and the simulation speed is very fast. And this is why this type of module is very useful for application including electronics or architecture design. You can imagine a typical PCB will have hundreds of components in there. So you want to have a tool which is very precise and fast at the same time. On the other side, we will have SC flow, which is use an unstructured mesh using polyhedral. And for these modules is used for application where you're very interested in reproducing the surface mesh of the surface of your object. So for example, if you want to analyze the flow over a wing, and this is why we're going to use it today for our analysis. Okay, so the outline of SC flow will start by a CAD model, which you import into the preprocessor. And I want to highlight you can use any CAD software to design your model. That includes SolidWorks and CATIA and Creo, etc. So any CAD model can be supported into Cradle. So in here we'll be defining the domain, and we will apply all the boundary conditions and material properties. And from this preprocessor, we will extract the mesh file, which is a GPS file, and the condition, which is a SPH file, and upload it into our solver tool, which will execute our simulation and give a L file, which is a log file with all the numerical results of the simulation. And additionally, obviously, apart from the numerical results, you will have the field file results, which you can import into the post processor to visualize them. Okay, so for today's demonstration, we're going to analyze a simple formula rear wing model. And the goal of this presentation will be to show you how simple and easy you can set up this model and run a typical CFD analysis. And obviously, the rear wing plays a very important role when it comes to formula computation, because it really supports the stability of the vehicle by creating a downforce. Okay, so some of the information obviously that you may require to create a CFD analysis will start from the domain. So you define how big your domain wants to be, and you define the properties and what type of analysis you're going to do, whether it is going to be a laminar, turbulent, and which turbulence model you're going to use. So this is the model we're going to replicate today. You can see here, this is the wing, which has a NACA 6412 profile. It sits within a domain which is air, and it will apply a normal velocity at the inlet to replicate the movement of the wing. And at the outlet, we will assume a 0 Pascal pressure because we are going to assume the flow is free from disturbances at the boundary of the domain. And on the sides and on top and bottom, we will assume a free slip condition where the boundaries do not affect the flow. Okay, so from here, I'm going to open the Cradle CFD tool. So first of all, I'm going to launch the kicker, which is so from here we can access all the module of Cradle. We have both SC Flow and SC Stream, and within both we can access the preprocessor, solver, and post-processor as well. And additionally, I want to mention about the user guide, which is a very important tool especially for new users. And here you have access to the exercises, so there will be examples of many simulation runs, and also you have references if you want to increase your knowledge regarding Cradle. So we start by click into the preprocessor module, and I'm going to bring it here. So I'm going to name the project name as for SAE wing, and we create the project file. And an important feature or very easy feature of Cradle is that you can simply drag and drop your CAD model into the user interface. So I'm going to do this. So here you can see the wing has been now uploaded, and you can see there's two components and the side plates. So I'm going to start by create a domain around this wing, and this is done by the navigation bar. You can see on the left hand side, we're going to follow from the top to the bottom all the steps they apply to us. So since we imported already our part, we can go into create parts, and we select, in this case, a cuboid, and I'm going to name it domain. And if I select the wing, you can either select it from the part tree in here or by just right clicking and selecting all parts. And if you go into calculate size from selected part, your domain will be built around this part. You can also preview it and see already a domain. In this case, we're going to increase its size since we want to make sure the flow is not affected by the boundaries. So in this case, I'm going to extend the domain. And if we look into the coordinates, I'm going to increase on the minimum y-axis by, for example, 1, and on the maximum side by 3. We can preview it, and you see your domain has been extended. We can do the same for the sides and upper and lower coordinates. So I'm going to define 1 on all direction. And as you can see now, your domain has been built up. For this type of analysis, since we're going to run a very simple case, we're now going to use a very huge domain. We're going to assume the flow is fully developed at the boundary of the domain. But if you were to run a more complex case, you will have to use a bigger domain according to your geometry. So once we're happy, we can also check this box where the domain is registered as a fluid region, and we applied OK. So now we have our domain ready. And from here, we're going to build our analysis model, which essentially divides the domain into triangles, and it will detect if there's any interferences with the geometry. So now we're going to the build analysis model, and we press OK. And we can go directly into the create facet. So you will see the domain will be divided into many triangles. And if there's no errors, if there's no interferences, there will be no error shown in here. So we are okay with this. So we're going to build the model. Okay, so now you can see this part has disappeared. If you want to, for example, return and make some changes to the geometry, you can always do this by returning to prepare parts command. So now the next part will be assigning material properties. So we're going to go into this. You notice there's an exclamation mark, meaning that the properties has not been assigned. So in this case, since we're only dealing with air, we're going to apply this in the domain. So we click into the domain, and the attribute will be fluid, and air is part of the gas group, and in this case, it will be incompressible. And we're going to apply this, and you can see the information being filled up. And for the wing, we're going to keep as obstacles. So now that we've done the part material, you see the exclamation mark has now disappeared. We're going to register the region where we can register surfaces. And this part is very important because you will need surface registration when you apply boundary condition, and also when you're going to do any mesh refinement. Okay, so I'm going to define the inlet of the boundary on the surface and just clicking on this, and I will name it inlet and hit register. I'll do the same for the outlet. It'll be outlet and register, and on the top and side boundaries, I will select them all together and call them wall. Okay, and additionally, we can also register the surface of the wing. First of all, we will need to hide the domain. We can do this from the part tree in here. You can uncheck domain, and now we have access to the wing. So we start by selecting the lower wing, and let me just deselect all faces to make sure we don't have any more parts selected. So I'm going to select the lower wing upper surface, and I'm going to call this lower wing upper surface and register it. And we can do the same for the lower surface. So just going to add it in here, and then we can select the upper wing upper surface, and finally the last surface remaining, which is the upper wing lower surface. Okay, we now register all the surface that we are interested in. Additional, we can also register numerical region at the rear wing, around the wing if you want to refine the mesh. To do this, we're going back to the register region command. We go into the volume region, and the target will be numerical region. And you select new. In this case, I'm going to select the wing pack again by right-clicking and selecting all parts. And we're going to make a cuboid. And if we calculate the size, the numerical region will be built around this wing. So we click this, and if we preview it, you can see there will be another domain created inside. We're going to just do a little bit of extension on the rear and on the sides. So I'm going to increase this on the y-axis by, for example, 2, and on the minimum y-axis 1. We can preview this prior to defining it, and can do the same for these side boundaries and top and bottom. Okay, and also you need to make sure to name this region. For example, I'm going to call it refine region. And once I'm happy with the dimension, I can confirm it, waiting OK. So here you can see your refine region has been created. Okay, so now we completed the register region command. We're now going into the conditions command. This is where we're going to apply the boundary condition, and we're going to define what type of simulation we're going to run. So first of all, in the analysis type, we have flow selected default. In the method settings, we can select which type of turbulence model we're going to use. This by default, we have SSTK omega, but you have the option to select many more models depending on your interest. And also in the solver type, we can change the solver type from pressure to density based in case you're dealing with supersonic flow. Okay, and in the basic setting, we do set up which type of analysis we're going to run, whether steady state or transit. In this case, for simplicity, we're going to assume the flow properties do not change with time, and we're going to keep the number of cycles as 400, and also we define the base pressure in here, and we're going to keep it as standard. Okay, so we now define which type of analysis we're going to use. I'm going to apply a flow boundary condition. Let me just check back the domain. So here you can see the surfaces we registered earlier in the register region command. And by selecting the surface, I can apply an inlet boundary condition. And I'm going to click into the inflow, and the type of condition will be a normal velocity. And for this example, I'm going to apply a velocity of 20 meters per second. And the turbulent intensity and ratio will be maintained as default. So I'm going to click set. And for the outlet, since we're assuming uh, the flow is free from interferences, I'm going to apply an outflow static pressure condition with pressure of 0. And on the top and side boundaries, I'm going to apply a free stream condition from the wall boundary. And here you can see the wall surfaces we registered earlier. And here you can select between no slip and free slip. In this case, we're going to go for a free slip condition. Okay, so we completed our boundary conditions. Now, if you're interested in the analysis control, you have access to many commands related to the matrix solvers, convergence criteria. So you really have room to play with this. And in the output setting, you can select which variable you want, additional variable you want to display in the post processor. And you have access to the, see, there's many variables that are already by default, but if there's any additional one you want to display, you have the option in here. And in the list file, this is where the numerical results will be uh, populated. And this is accessed through the log file. So in this case, I'm going to uh, list an additional parameter. Uh, so we want to output the surface force on the wing uh, because it's very interesting if you want to extract the lift coefficient, drag coefficient. So I'm going to go into surface force and new. And here you can see the surfaces we selected, we created earlier. We can select them, all 4. And here we will just keep the cycle interval as 1. Okay, so now that we completed this, we can now proceed into creating the mesh. The mesh in Cradle is done in 2 steps. First of all, we create an octant where the domain is divided into cuboid-shaped octant, and then following that, we will create a polyhedral mesh in the mesh command. The good thing about the octree parameter is that you can visualize how your mesh will look like in a very fast time. So for example, if you're going to make any refinement, you can see those within seconds instead of waiting for the whole mesh to be created. So if you go into the octant parameter, and in this case, you have the option to input a number of elements that you want to target or minimum size. In this case, I'm going to define by myself. So if you go into octave parameters and details, I'm going to restrict the maximum octant size on both maximum and minimum. So I'm going to make a very um, fine mesh. So for example, we can put a size of 0.03 for both maximum and minimum. And then if we go into the region, we can refine the region where we want the machine to be more dense. So in this case, it will be obviously the wing surfaces and also the numerical region we created earlier. So start by the numerical region. In the basic setting, we put a 0.03. So for example, we can do it by off and we hit apply. And for the wing surfaces, I'm going to select all 4 by keeping a control button. And for example, I'm going to make it even more refined. And also I'm going to apply an influence range. And this is basically is used to propagate your octree define how many layers you want to propagate your octree. So in this case, I'm going to apply 2. So you hit apply, and when you're happy with this, you can create your octree, and you see within very few seconds, your octree will be generated. And if you're happy with this, you can then proceed into creating the mesh. So process should be done in a very quick time. You can see here the information are filled up in the message. You see number of octants and nodes and elements. And from here you can see the octree has been created. So we can close this. And we can also see a cross-section very briefly from the view cross-section view. In this case, it will be the YZ axis. And you can see, in this case, you see this is the numerical region. In this case, it's probably been created way too large. So you can create maybe a smaller region. And you can see the refinement around the wings. Okay, so once you've done this, you're going to create the mesh, and this is where you define the number of prism layers, and these are used if you want to evaluate the boundary layer and flow separation as well. So for this type of study, we're going to keep only 2 layers, and if you were to run a more intense study, you might need to increase the number of layers. So I'm going to open a model which has the mesh already computed, since this process may take up to 10 to 15 minutes. So let me open the model for you. So here you can see, there you go, that's the mesh. And previously when I did the region refinement, I created a smaller one. So this, you can consider this as the numerical region. You can see here the cross section of the mesh, the polyhedrals, and also you can see the prism layers on the wing surface. Okay, so once we're happy with the mesh, you can also extract the information. If you go into the mesh and click into show mesh information, you can see here at the bottom all the information that you may require. So once we're done with the meshing, we can proceed into the execute. So in this command, the software will export the meshing file as well as the condition file, which are important for the solver. So I'm going to open the solver command. This is done again from the kicker. So previously we done the preprocessor. Now we're going to launch the solver from this icon. And then we're going to upload the SPH file onto the window. So just a few seconds while the software opens. There it is. You can see here, you can, as done previously, you can either drag and drop your SPH file onto the window, or you can open it from here. So in this case, I'm going to drag and drop it. So if you open the case and the SPH file, can just drop into the window. You can see here the status of the of your case. So at the moment is in waiting. So to launch your simulation, you can simply go into execute and you launch your case. So to save some time, I'm going to show you how this window will look like at the end of simulation, which is here. I'm sorry. Okay. So, okay, let me expand this. So here you go. You see the status has changed to steady state. You can see number of cycles on the x-axis and the fluctuation of the residual in logarithmic scale on the y-axis. So in this case, we define that once your residual reaches a value of -3 altogether, the simulation will complete. So once we've done this, there's a useful command to access the log file directly from the solver, which is in here. So if you click into the L file, you will have access to a very useful tool for your numerical analysis. So this is the log file. You can see here you can see a number of cycles, and you can jump between cycles and see the variables that you will need. So earlier we did export the forces value in the output of list file, and here you can see the forces listed as number. And if you double click on a value, you can also visualize the graph. You can see here it has converged, and you can also select different variables and select them on the same graph by pressing Control and clicking on them. And you can also export these files and all the data into a CSV format, which might be very useful for your results comparison. Okay, so I'm now going to open the post-processor. Again, we open the kicker and we launch the post-processor from here. And there is the post-processor window. In this case, the output of the solver will be an FPH file, which we will find under the same directory where we have all the other file exported by Cradle. So you can, again, drag and drop the FPH file, or you can upload it from here. So let me open the FPH file in here. So within very short time, your model will be created, and you can see in here the wing and the domain has been created. So there's a plane already created in here. You have the surface, and we can plot a contour of the, for example, the pressure on this surface. So we check the display button, and here we select the variables we're interested in. So I'm going to go for the pressure, and I'm going to select the redraw button. And here you can see there's a plot of the pressure. Here you can see the color bar, which you can customize as you wish just by either clicking here or double clicking below. You can change the color scheme, you can change the font size, the position, and many more settings. I can show you briefly another contour, for example, the velocity on this surface, and we redraw, and you see how the flow velocity is changing as he approaches the wing. Okay, so to save you some time, I've also created a file which contain a more detailed figure. So let me upload this to you. So in this case, it will be a status file, which I have here. So let me drag and drop. And here you can see you have the contour on the cross section of the pressure. You have the velocity, I'm sorry, and you have the pressure contour on the surface of the wing, and you also have some straight lines. So this will be can be very useful when you create your reports. It's very simple to create this type of images. We have many commands here to create planes and surfaces, and you can also select points, and you can also create streamlines from this command. Okay, so I'm going back to the slides. So here you can see we recreated this modeling here, and I'm going to move on onto the next case. Okay, so here you might be interested of doing any further analysis. For example, what will happen if you change the angle of attack of one of the wings? So to do this, it's a very simple process. You will have to return to the preprocessor, and if you hit the modify parts and the transform command, you can tilt the wing by the number of by the angle you want to increase, and then you just by clicking onto the execute button, which was on the bottom of the navigation bar in the preprocessor, the software will automatically redo all the process for you. Okay, to save you some time, I already done this before, so I'm going to show you the results. We have the results in here in the presentation. Here, for example, you can see the pressure contour between the original case and the modified. In this case, I modified the angle of attack by 8 degrees. So you see the pressure variation between the two. It might not be extremely clear from this contour, but I can show you some other ones. But in general terms, what happened if I increase the angle of attack, the surface in contact with the air is less, so obviously this will decrease the pressure and subsequently also the downforce. So if we see the velocity contour, you see similar behavior. So there are some differences, but they're not completely clear from between the two. And if we see the pressure contour of the surface, you can see how the pressure has changed by just increasing the angle of attack of the upper wing. Okay, and finally, if you were to analyze a full model of a Formula vehicle, you will have to make some changes. For example, the domain will have to be obviously bigger, and it will have to account for any flow interferences from the front wing and the tires and the vehicle body as well. And additionally, when it comes to meshing, we have a very powerful tool in Cradle, which is the voxel fitting mesh, which can really fit a mesh even for such complex geometry. And if you want to, obviously, given the increased geometry, you're going to apply some best practices tools. For example, you're going to refine the region you're more interested in, so you can save some number of elements, and subsequently you can reduce your simulation time. Okay, so now that you've seen Cradle, there's a very interesting feature within Cradle, which is the co-simulation. Once you do your thermal fluid analysis, you might incorporate with other Hexagon products. For example, you can evaluate the acoustics and noise using Actren, or you can run a FEA study using Nastran. And if you're going to follow our next webinars, you will also have an overview of the softwares as well. Okay, so Alex, if you want to comment on the how to access the software for.
Yeah, sure thing. So good news, our software is available for free. It is free if you are on a student competition team. So there's a student competition bundle. You have to fill in a form. We give you access to the software packages we have listed here. Those are the full commercial releases. Notably, if you want to use Adam's car, you're going to need to go through the student competition bundle. If you're not on an official team, and again, it doesn't have to be a formula team, it really can be any team that is involved in some kind of engineering competition, that would make you eligible again for the first bundle. If you're not on such a team, then you would be looking at using our free student editions. Those have limited model size and there are fewer packages available, but they are still really great if you are getting started with simulation. And really, for the first few exercises that you're doing as you're learning simulation, those can get you pretty far to really far. So that's how to get at the software. Again, we're doing these webinars 1 a week for the next 5 weeks, so 6 total. Next week, we're going to be talking about powertrain development with Romax. Romax is specialized software for building gearboxes. So you can do things like just drag and drop gears onto a view and have dragged out some shafts, and Romax will really quickly figure out like how those gears should be meshing, how do you set gear ratio, and ultimately you can do gear rating calculations. Um, they are, it's useful for other types of machine elements too, like bearings, and we'll be focusing on planetary gears next week. After that, we will have 3 weeks focusing on Adam's car, going really deep with that, and wrapping up with a webinar on finite element analysis. The webinars, if you aren't able to make it, or what have you, want to be able to watch it later. Maybe you're here now and you do want to access the tutorial information to try again tomorrow. We're going to have those going up on our YouTube channel, and you can follow me on LinkedIn for subsequent updates on what's going on with the webinars, registration links, and so on. Oh, and I would say that if you are watching this on a recording, you can access all of the links that I mentioned in the description here on YouTube. And oh, the part file that Shiraz used and maybe some other supplemental files are going to appear on our webinar homepage. There's a link to that again in the chat. I want to just call out Reese, who's going to be presenting next week, says that we do have a little bit of an error. Romax is not yet listed on the list of student competition software here, but you actually will get it. So let me know what questions you have specifically about accessing the software. That's something that I do a lot to help out with here at Hexagon. Shiraz, I'll let you wrap up, and then I'll be around to help moderate the Q&A.
Perfect. Thank you, Alex. I hope the question, if you have any question, I hope the presentation gave you like an overview of the software and how to set up the model. And let me know if you have any question. You can unmute and ask question. You can also type in the chat box. Okay, thank you.
So Shiraz, I see a couple of questions.
Sure.
One from, I think it's Paul Nasser. Does Cradle offer part repair features to repair knife edges, remove or solidify elements, etc.?
Okay. So hi Paul, yes, we have a tool in the preprocessor where we before we build the analysis model, the software creates some facet, and if there's any, let's say, geometry interferences, the software will try to repair them. You might lose some quality when doing that, so but we definitely have this tool which you can use prior to building your analysis model.
Would it be beneficial, question from David Misaros, would it be beneficial if we use a solid-based mesher instead of voxel fitting mesher for the full simulation?
Yes, that depends on your geometry. If your geometry is fairly clean and you don't need to do a lot of manual operations to clean it up, I would say it's fine. It's probably be okay if you go with solid-based mesher. Where the voxel fitting mesh shines is if you have a lot of surface errors and interferences, gaps and things like that would take you a long time to clean up manually. The voxel fitting mesher is really powerful in taking care of those surface errors automatically during the meshing process. So to answer your question, I think it depends on what level of CAD complexity you have and how clean your geometry is. But certainly we had flexibility of both options within Cradle, within ISFlow.
And I see, Rodrigo, that you had actually asked, how long was the solve time for the simulation?
Oh, yeah, apologize for not mentioning this. In this case, it took me 30 minutes to run the case. Obviously, depending on your computational power, it might take longer or shorter time, but an estimate will be 30 to 40 minutes for the simulation and 10 minutes for the meshing.
So it's not like you need a supercomputer to get some real work done.
Exactly.
So I see some questions in the Q&A, some in the chat. From Logan Ruhlman, does Cradle also do thermal analysis for the intake and exhaust system, for example?
Absolutely. Apart from the flow analysis, we have thermal analysis. You can do this using both SC stream and SC flow, and you can do your, for example, your intake analysis very precisely. I would recommend probably using SC flow given the shape of your intake system, which might have many ducts. So it's definitely possible doing this.
So I've got a couple of questions. So you mentioned prism layers. What do prism layers do?
Okay, so essentially your surface of your geometry will be divided into layers, and this will be very useful when you, for example, want to evaluate the boundary layer because your surface will be very refined around that region. So apart from the prism layer, the SC flow creates some polyhedral mesh, which covers the volume of the of your geometry. So it's a very useful tool when dealing with aerodynamics and evaluating boundary layer and flow separation, for example.
Do you have any rule of thumb on how fine the mesh should be? You also had a 0.03 number for the octants. Can you just, do you feel like that's going to just generally work well for everybody, or what would make somebody want to adjust that number?
Well, you can obviously, sorry, Rodrigo, did you want to respond to this?
Sure. I would say, so there's not really a general rule of thumb for any geometry. The rule of thumb is it'll depend on the size of your geometry and the complexity. So 0.03 basically depends on, say your wing is a meter long. You want to discretize or resolve the wing to have more elements, say 50 elements along the length of the wing, 50 to 100. So the size depends on the size and curvature of your geometry. In this case would be the wing. Now, in terms of how fine or coarse the mesh can be, typically you would start with a relatively coarse mesh that resolves your geometry properly. And if you can then proceed to refine the mesh to see if the result changes successively. So the 0.03 in this case was defined so that the wing curvature and surface was properly resolved within reason. I don't know,
Great,
I think
thanks.
that was all. Yeah.
Yeah. I see a question from Ryan Hirsch. Can Cradle test moving parts like wheel rotation?
Yes. We can. So we have different methods to apply moving elements or to apply rotation into the model. So we have methods that apply basically source terms into the momentum equations. The actual mesh is actually not moving. That would be what is equivalent to the moving reference frame approach. We also have the actual sliding mesh approach where the mesh is actually moving and the elements are rotating. And also we have overset mesh to account for any other motion that you may want to apply to your modeling.
I see an interesting question from David Masaros, and I have some thoughts on it. I would like to hear from you first, either Rodrigo or Shiraz. So Shiraz, you'd mentioned COSIM. Would it be an idea to couple your full vehicle aerodynamic simulation to a full vehicle dynamics model in Atoms so that you can analyze the effect of pitch sensitivity on the aero?
Do you think Rodrigo can answer to this question?
Yes. Yes, you can. We can couple Cradle with, as it was shown earlier, with a couple of different of our CAE tools. One of them being Atoms. So if you want to, Atoms will dictate the motion of the parts, and we can account for that motion in Cradle to see obviously some motion of a wing, for example, will probably change the flow. And so, yes, that is possible. Just to take a step further there, for example, a very common analysis and formula is FSI, right? We're trying to maximize the force from an aerodynamic perspective, but also we need to keep in mind that that will add additional force to the structure. And so we have the ability to couple it with an FEA tool to also take into the account the structural performance of the wing. So that's one of the nice things about Cradle and CoSim, our co-simulation platform, that is very easy to couple with other SAE tools.
Is MSC CoSim needed to be able to do the coupling between atoms and Cradle?
Yes, that is correct.
Okay, so there are two different ways to set up your license bundle. So if you request a student competition bundle and you really are interested in this kind of CoSim capability, be sure to ask about that. We would need to just make sure that you're using a licensed server as opposed to using another approach. Another thing that I would add is like, hey, if you really want to do this CoSim, knock yourself out, go for it. Still, if you're not sure, I wouldn't stress over not doing it. When I look at what formula teams are doing, it seems like in general they're not doing really heavy CoSim, and I know that it is just a scramble to get the analysis done at the start of the year so that you're then ready to just jump into build. And so having really practical models that can answer some questions for you, that's really useful, but it could be kind of challenging from a team dynamics standpoint and just like project management and scheduling to be able to get all of those models up and running and integrated in the time that you have available. Plus doing that kind of CoSim or like looking at what's the behavior of the vehicle over time, that could be really challenging. What I would say works really well when linking our products and is, I think, much less of a headache is to, for example, you could do a bunch of different Cradle runs where the overall wing is held at a few different angles and kind of get a curve of what are the drag forces as a function of angle, and you could get that imported into atoms. And so that way you wouldn't need to do a lot of time varying CFD to do the vehicle dynamics modeling that you would want. My point is that there are simpler ways to connect our products than doing everything linked up all at once, but sometimes that is valuable. And again, if you are interested in doing that, there are ways that you can do that with our student competition bundle. Can Cradle use the outlet surface data in the next iteration of the inlet data? Ryan, I wonder if you're asking about a periodic boundary condition, or Rodrigo, do you want to take a whack at this one?
Yeah, I was going to ask if that was the case, if it was about a periodic or if it was more of a mapping a boundary condition or using a previous simulation, the result from a previous solution to use as the, say, initial condition or boundary condition of another new simulation. But either way, if it's the question is related as
Ryan's saying periodic.
Oh yes, so yes, we certainly have periodic the ability to use periodic boundary conditions. I would say in the context of say formula SAE, say if you're doing a running a yaw angle configuration, but you don't necessarily want to rotate the vehicle for every single angle that you're testing for, then periodic boundary condition is certainly a way to do it, where you're just modifying the inlet angle, the inlet velocity component angle. And in that case, using periodic boundary condition would be certainly the way to go to avoid having to rotate the vehicle for every angle iteration. So to answer your question, yes.
And overall, oh, I see another question. How would you suggest balancing, this question's from Paul Nasser, how would you suggest balancing time investment in creating simulations of individual elements, like a rear wing in isolation, as opposed to simulations of the entire aero package? The complete picture that you get from simming the full car is important, but of course, sims of individual elements is much less time consuming. I feel like a lot of the answer to the question is in the question itself there, right? That there's a balance between model fidelity and model speed based on whether you're modeling pieces or the whole thing. But Shiraz or Rodrigo, I wonder if you have further thoughts on this point.
I would say, yeah, I mean, I would say it's a balancing act of how much time you have and also the number of iterations that you want to go through, as well as say your computing resources. So I would say maybe general rule of thumb is at early stages where you have say 10 wing options for designs and where you want to focus only on the wing, I would just do maybe comparative studies of just the wing components, and based on say 10 designs, you narrow down to 3 options that are likely potential for the best balance between maximum downforce and drag. Then I would move on to maybe full vehicle analysis for just you know, two or 3 of those options. But yeah, I think it just depends on a lot of other aspects, but maybe that's a general initial overview of how I would approach that.
And Shiraz, can you point us toward, I mean, we've had just a lot of really great questions in the Q&A here. If people wanted to know more, right, like we've said, you know, in general, here's how to do it. How can they dig deeper and learn more about Cradle's capabilities with respect to these features?
We have many resources available in Sim Companion. I believe they have access to that, as well as in the Cradle CFD user guide. There's many work example available in there, where some of the cases are very similar to the Formula vehicle design. So you can get a lot of inspiration and increase your knowledge on that. And also we have some video tutorials available as well, which might be more probably interactive rather than reading a manual.
Well, I think with that, we are, you know, about at time. We've had just a huge number of really great questions. I don't see any more coming in. Thank you, everybody, for coming. Shiraz, thanks for preparing such a great and polished, detailed presentation that I think just has a lot of really useful advice. And Rodrigo, thanks for your help with answering these technical questions. All right, well, thanks, everybody. I'm going to end the call now, but I really appreciate everybody's participation. Thanks. Bye.
Bye. Thank you.